Welcome to electron configurations video number 3. And we are going to look at some examples from your homework packet on page 11. But I think I just want to look at the possible charts on either page 9 or 10 of your homework packet. Make sure you know how to use these tools to figure out electron configurations. So here is the deal. In the first row or shell, there's room for 2 electrons. We call this 1s2. And then we go up for the next shell, it has 2s2 and possibility for 2p6. So there'd be a total of 8 electrons in the next shell. On the third shell, we go 3s2 and 3p6. So again, there's 8 more electrons possible in the third shell. The next shell, we go to the lowest thing, which is 4s2, and then 3d10, 4p6, which is 18 electrons. In the fifth shell, we go 5s2, 4d10, 5p6, which is also 18 electrons. Okay, when we get to the 6 and 7 shells, the 6th shell is 6s2, and then it's the 4f14, those ones on the very bottom, 5d10, 6p6, for a total of 32 electrons in the 6th shell, and then 7s2, 5d4 or 5f14, 6d10, and 7p6 for the 32 possible electrons in the 7th shell. How does that compare to the periodic table? Let's take a look at that. And let's see if we can share this here. This works the same way. It's just a different visual for how that goes. So you can go, first shell is 1s2. The next shell is 2s2, 2p6. The third shell is 2s2 or 3s2, 3p6. The next shell is 4s2, 3d10, 4p6. That takes us through shell number 4. Energy level 5, 5s2, 4d10, 5p6. And then the 6th one is 6s2, and you got to sneak this in up here, 4f14, 5d10, and 6p6. And the last one is 7s2, 5f14, 6d10, and 7p6. So it's the same as the other chart going bottom to top. It's just more in a periodic table way of seeing that. So whichever tool works, or a combination of both, that you can figure out these problems. Let's look at the problems that we want to right here. And it's going to take me a moment to find this. Bring this up. Okay, so this would be page 11 of your homework packet, and I'm asked to do electron configurations. So really, it should go 1s, and then above it should be 2s, and then over to the side, it should be 2p, and so on. The reason I'm trying to do it just all in a line is strictly for space-saving format. So that's why I'm doing this, but it goes in the same order as projected. Oxygen has 8 electrons. There's going to be 1, and I'm going to do an up arrow here, 1s1, 1s2. Okay, we still got 6 more electrons to go. So I'm going to fill the 2s, and I'll do an up and a down. And now I'm going to go to the 2p, and there's room for 6 electrons, but I only have 4 left. 1, 2. Notice I'm following Hund's rule. I'm going to keep them in their own rooms until they're filled up. Okay, I've got the 7 electrons. I'm going to have to pair somebody up here. So I'm going to pair this one going down. It's pretty hard to, there's not much room to write these in. I realize it, but this would be the answer. 1s2, 2s2, 2p4. And that would be my answer for oxygen. I'm going to go to F- down here and do this one. Fluorine has 9 electrons and 9 protons. But the F minus ion, why is it F minus? Because it gained an electron. So I'm going to do it for actually 10 electrons. And I'm going to put them in here, one here. And I'd like to do this a little faster, but it just doesn't go that fast with this thing here. 1s2, 2s2, that takes me to 4. I'm going to go 2p1, 2p2, I'm kind of doing my up arrows, 2p3, and then I'm going to fill it down 2p4, that's supposed to be an arrow filled there, 2p5, and 2p6. So I might just redraw this one here so you can see it. Still can't see it. So 1s2, 2s2, 2p6. These are completely filled. Actually, this is the first shell. These two combine to make the second shell. You got 2 shells completely filled. The F minus ion now becomes like the noble gas neon, which is a very stable electron structure. Okay, what if you get to these, to this, it says what atom is represented by different things. All right. So all right, I'm going to better erase these things here real quick. Sorry about that. And let's answer these questions here. So this one, we're just going to count electrons here. 1, 2, 3, 4, 5, 6, 7, 8, 9. It says atom, so it's not an ion. What atom has 9 electrons? It is fluorine. So we can get the F, big F right here. Okay. The next one is I'm just going to look at this one. This one's kind of weird. 1, 2, 3 electrons. Well, I know 3 electrons is lithium. Why did it skip a spot? I'm not going to ask you about this on a test. This is what we call an excited state. This is how Bohr actually knew about these electrons moving around between energy levels. You plug a current into a gas, the electrons go to excited states, they fall down. You see bands of light, you can measure the energy. Okay. Typically, how you're going to see this is 1s2, a 2s1. You count the 3 electrons, will be done. I'm not going to ask you about excited state on a test, but this would be lithium in the excited state because it still has 3 electrons, but one of them skipped. Okay, and I'm just going to say excited and very slowly write excited like a sloth. That's kind of silly. Okay, I'm going to go to the next piece here. And I think I got to do a little erasing to go here. Let me see, get rid of these things. Let's try one of these down here. And I'm going to go to, oops. Sorry. Okay, I'm going to go and do bismuth. Now, if you look at it, bismuth has 83 electrons, and that's going to be a lot. But there is a shortcut here, which I want to show you. So just going back here, and I think I'll go to our structure chart like this. No, that's not the one I want. We'll go find bismuth again. And we'll find it here. Okay, so bismuth has 83. And I could actually, I know it's going to be somewhere right in here. There's going to be 83 electrons. Instead of doing everything up through xenon, so I look through xenon, I could write out 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6. I can take a shortcut. And that shortcut is writing just xenon and then continuing at the 6s level and then go to the 4f and the 5d and the 6p is needed. So that's what I'm going to do in this example as I go back to it. So I go back, I'm going to find this thing here. I think I'm going to find it here. And I'm going to write right here, xenon. So for the bismuth, I'm going to write xenon. And that's the first 5 shells that we're covering. And after you look at the first 5 shells, what comes next? It's 6s2. And then there's the 4f14. Okay, so xenon is 54, plus 2 is 56, plus 14 is 70. I need to get to 83. Okay, let's see, we're going to do 5d10. That takes me to 80, and then it's going to be 6p. And I think we're going to go over, what do we have? 54, 56, 70, 80. 6p3 would be 83 electrons. This would be the electron configuration for bismuth. So instead of writing everything up to the noble gas core, I use the noble gas, and then I continue from that point right there. You want to look at those charts and verify that that works for you. Okay, the final piece that I thought I'd take a look at was just what atom is represented by each electron configuration. So these are pretty easy. You can count the exponents. 2, 4, 10, 12, 17. It looks like we haven't skipped anything in order. Things have gone right. Which element has 17 electrons? That would be chlorine, for example. All right, if I went further down the list and I see something like this, and I see Kr and I see 5s1, I can say, oh, krypton, that's through shell number 4. That has 36 electrons, and it looks like I'm adding the next electron. That would be 37. What element has 37 electrons? You're going to find out that that is rubidium. So that would be how to handle these types of questions here. All right, I think that's some practice opportunities. Look at page 11 and 12. There'll be a key that shows a lot of these answers too. Good luck.